And thanks for joining us for the first half of Monday, March 27th lecture in the video format. And then again, sorry that I'm away for the conference here, but let's see. I think we left off with going over the enamine formation mechanism. And what we want to do, hopefully you kind of did this informal homework. We wanted to fill in the blanks here. The first example or problem we have is about figuring out the starting material for this enamine formation. And this would be a good example to think about because the example earlier was from starting with a ketone, and here's hopefully you could tell that this example is about an aldehyde starting material. One of the ways we would know that is because this carbon right here was the carbonyl carbon, and it has a hydrogen, so that makes it an aldehyde. Okay, and this right here was our secondary amine. I guess I could say was. Okay, so the starting material, what would it have looked like? It would have looked like this aldehyde, and this is the secondary amine. Really good study for this would be to see if you can propose the right mechanism for this enamine formation. And just to avoid redundancy, we're not going to do the hydrolysis mechanism in class per se. It would be the exact opposite of this mechanism here. Starting with this structure, enamine would get a proton at the alpha position like so, and then you go step by step backwards. That would be the mechanism here, okay? So let's think about if we did try to do an hydrolysis of this, what would be the product? I want you to see that this is going to be the ketone carbon in the end, and then of course this right here would be the secondary amine, which means that the product ketone after the hydrolysis should look like that, plus this 5-membered ring amine. It's called pyrrolidine. The other one here is called, this is piperidine, and then this is pyrrolidine, but that would be the product there. And even though we said we won't go through the mechanism, I just want you to know that the first step will look like, because a lot of things, once you get through the first step, you could usually figure it out, right? So after the first step, you would get this intermediate. And this is basically like protonated imine or iminium ion that water could attack here, like so. So, and then that's how the hydrolysis mechanism goes until the ketones regenerated, and then amine is freed. So hopefully you can figure that out. And if you get stuck, you could refer to the imine hydrolysis mechanism here, right? Like water attacks the imine, and then you get to the tetrahedral intermediate, move some protons around so that you can free the nitrogen, and then you end up with a carbonyl compound. So basically the same idea. Here, just to help you out with the very first step, I guess, that's the idea, okay, to get to that intermediate. So please definitely work through the mechanisms that lead to those from the for hydrolysis of enamine, as well as that one example of enamine formation from aldehyde. Now, one of the last types of reactions we want to talk about for aldehydes, ketones, is Wolff-Kishner reduction. And this is a very useful type of a reaction because this is not like many other reactions we've talked about. You actually get to sort of remove a functional group, which most of the time that's not very useful, but because functional group is where you can do chemistry, so often you don't want to remove them, but sometimes you just need a alkane. So this is a useful thing to have in your toolbox as a synthetic chemist. This goes through a functional group called imine or hydrazone, which is an imine from hydrazine. And I can't remember if we talked about the molecule hydrazine before, but it's kind of like the cojoined twin of ammonia. It looks like this. It's a very nucleophilic amine because the two electron-rich nitrogen atoms are connected together. So this is called hydrazine. It's a reagent you definitely want to be aware of. I think a couple of you have hydrazine as a reagent or starting material in your synthesis project. So as we said, it's a very nucleophilic amine, so even without the carbonyl being activated, it could definitely add to the carbonyl via nucleophilic addition, which will of course create that tetrahedral intermediate. And hopefully you can tell that it would be a very good thing to quench that alkoxide O negative and then quench the N positive ammonium cation there just by moving protons. So now we have this neutral intermediate. Nitrogen regained its lone pair, which nitrogen, the main thing about nitrogen chemistry is it's always willing to use that lone pair to do something with it. So it could definitely, for example, kick off the hydroxide, and you might have some reservation about doing so in the mechanism because hydroxide is not a very good base, but it can immediately become a neutral water by getting that extra proton off, so that is not an issue here. Okay, and so this is what's called hydrazone. Okay, and once we get to this intermediate, oh man, I need more space. I'm just gonna rearrange a couple things to make more space. Once you get to the hydrazone, which is an imine, excuse me, so the reaction actually can't continue because we have sodium hydroxide in the mix. And I should probably draw these out. So there's a bunch of strong base hydroxide in the mix, so at any given point this could happen. It's not a very favorable acid-base reaction, but as long as it's possible, it happens to some extent. That's why these are all reversible steps. And the reason why I might draw this particular anion intermediate is because if you think about the resonance of this, right, you have negative charge on that carbon, which that's a very strong base, so it could easily take off a proton of water, like so. This would be an irreversible step, essentially. And where we're going with this, maybe you can begin to see it right around at this juncture. We're beginning to see something that is beginning to look like a nitrogen gas, which is a very stable molecule that could evolve away. And so that actually is the driving force here that removes this functional group. Because if another proton gets removed by a strong base, right, we have this situation, which of course if that extra lone pair gets shared between the two nitrogens to leave behind those electrons, so that this could evolve away as nitrogen gas. Remember that upward arrow means evolution of a gas, and once this grabs a proton from water, now that's the product, right? And so that's how Wolff-Kishner reduction works. It's a lot of steps, but if you think about what's going on, really we just showed a basic base catalyzed imine formation, and from there just removing a few protons from nitrogen, and then passing back protons to the carbon, and in the end the nitrogen gas evolution drives the reaction here. Okay. And this could be useful, like I said, if your goal is to make an alkane compound from functionalized things. So here's an example where people have been able to make an interesting molecule from this natural product called alpha pinene. And just like the name suggests, this is like part of the smell that you notice when you're in a pine tree forest and whatnot. So this question's asking if this is subjected to ozonolysis first, and then Wolff-Kishner reduction, what would be the product? So once you do the ozonolysis, remember here's an alkene that gets cleaved like so. So the product of that should be this aldehyde and this ketone, right? And Wolff-Kishner reduction can essentially replace a carbonyl with an alkane. So what does that mean? If we use excess hydrazine, so that we have enough to react with both that aldehyde and this ketone, we should end up with an alkane. Oops. Alkane there and alkane here. So we actually now get a symmetrical molecule because this is the same as those two ethyl groups assist each other. And just so that you can keep track of the carbons very well, this ketone carbon is right there, and then this aldehyde carbon is right there. Okay, so hopefully that makes sense. That's just another example of a Wolff-Kishner reduction. Again, really useful going from carbonyl to alkane. And along a similar line, meaning like reduction type of a reaction. This should be just a review of something we've done before in the alcohol chapter, but remember aldehydes and ketones can also be reduced by hydride source like sodium borohydride or lithium aluminum hydride. Now here in this context, the only thing I want us to carefully think about this reaction that we've learned already is which functional group is more reactive between aldehyde and ketone. Remember that aldehyde is more reactive, so that means that the first product that you're going to form as this reaction progresses is that the aldehyde gets reduced, but maybe the ketone is untouched. So this is after one equivalent of sodium borohydride reacts. After if there's excess amount of sodium hydride, then you would end up with this racemic aldehyde, alcohol, dialcohol. Right, so that's the only thing we wanted us to think about that. And that works kind of the same way with whether it's hydrogen nucleophile or carbon nucleophile, which is what Grignard reagents are. Maybe we'll say carbon. So the first equivalent of this ethyl magnesium chloride, or aka the Grignard reagent, would react with the aldehydes. So I would say that if this is done with one equivalent of Grignard, this would be the product. But with two equivalents, of course, both of these functional groups can react with each other. So, I mean, react with magnesium, or what am I saying, with the Grignard reagent, so that we could expect to see that tertiary and secondary alcohol products as a result, right? Okay, hopefully that makes sense. And then here's another carbon nucleophile example. We already talked about cyanohydrin formation earlier, but hopefully you could fill in the blank here. Maybe pause the video and then see if you can figure out what would have been the study material to get to this cyanohydrin product. And it would be this aldehyde, which hopefully you know how to name that. That would be benzaldehyde. But in this context, we're not just revisiting it. I just wanted to tell you that this is a very synthetically useful maneuvering because that cyano group is very useful, synthetically speaking. You can reduce it to gain amine, and we'll talk about the mechanism later and not here. So that's one thing that nitrile or cyano group could do. Another thing that it could do is to hydrolyze and become carboxylic acid eventually. Okay, but the mechanism here is kind of complicated, not complicated, but would suit better in chapter 21. So for both of these reactions, I'll refer us to what we're going to cover in chapter 21 for the mechanism. For now, I just want you to kind of be familiar with the results. If you want to have, this is one way you can make an amine or carboxylic acid, is reduction of nitrile, or hydrolysis with acid of nitrile would give us that. In the final video for chapter 19, we want to cover the Wettig reaction, which is going to be a very fun and exciting a new type of reaction that we'll cover. So see you in that new